It's a great pleasure to be here, and it's really amazing to see many new faces. So, young generation, you're amazing. That's great. I will talk about joint work with Elden, Almanto and Denis, Nardin. And so the main ideas of our work have been developed before by Bruno, Kahn and Marc Levine. And so what I will tell about is the main result that they proved and explain a bit about how we generalize and partly simplify what they have done on twisted motivic spectral sequence with relation to twisted K-theory. And okay, so to bring you to this subject, I will recall some things that you have already heard in the summer school, but they appeared in different talks occasionally. So let me quickly recall what brought people to the motivic spectral sequence before we talk about twisted version of the story. So it all started in topology with a T-Hirzebruch spectral sequence. So when you have a CW complex, and then you have a T-Hirzebruch spectral sequence, which tells you that you have singular cohomology of X with coefficients in topological K-theory of a point that converge to actual topological K-theory of X. Okay, and so the nice thing about it is that topological K-theory of a point is pretty simple, so it's either integers or 0, and so this allows you to compute topological K-theory in a nice way. And why this appears? Well, one can think about this spectral sequence in two different ways, which give you the same spectral sequence. So the two equivalent reasons are once you can stratify your CW complex. So you can look at the skeletal filtration on X. And this will give you a spectral sequence. And the other thing is you can forget about X and look at the topological K-theory and look at the filtration on the topological K-theory spectrum. So you can consider the, okay, I always want to call it Postnikov tower, but then I'm reminded that it's the Whitehead tower. So if you think about this topological K-theory groups as, let's say, so you took mapping space X into KU and to 0. So if you think from that perspective and similarly about singular cohomology, then you can consider the tower of KU given by so it's connective covers and okay and so on, and then you can take the slices and so the cofibers are the slices.
So what is F2, F1, F2, this is...
Okay, so that's the universal and connective spectrum associated to K. And so what saves us is that the slices are computed in an easy way. So the nth slice will be just the suspension of the Ehrenberg-MacLane spectrum. So it will be at 2n suspension of the, let me denote it, the topological Ehrenberg-MacLane spectrum, where, so these integers here are the, okay, I don't know how you think about integers, but it's actually the 2n homotopy group of K. So that's why they appear here. And so again,
this is an even.
Yes. So
in odd it vanishes, or
yes.
So, but you wrote S. It should be S2n, no, or something involved.
If you, so I think it was explained before that you want to speed up this spectral sequence by deleting zeros.
But you also have negative. I mean, with the spectral sequence, you have.
I think, so in algebraic geometry, sure, in topology, I thought you're good this way. But feel free to correct me. Anyway, the computation of slices gives you the, no, it's not. Gives you the spectral sequence.
You can filter in two directions.
Okay. Well, anyway, you have both periodicity, so you can figure it out. Once you know S0, you're good to compute other slices. Okay. So the main thought so far is that you have these two different approaches that give you the same spectral sequence. And now, what does it have to do? So what is the twisted version of that? So classically, you can look at twisted version of topological K-theory. And so how do you do that? Well, you consider, instead of usual topological vector bundles, you can twist the gluing functions by a cocycle. So you can fix a cocycle which will then live in H3, and so twist the gluing functions by it. So okay, and so this will, okay, out of this you can get twisted topological K-theory groups, and you might ask, okay, so is there a version, like twisted version of this spectral sequence? And the answer is yes, and actually it happens so in topology that the spectral sequence will have the same terms, but the differentials will change.
So the lambda in H2, in H3, and we consider complex.
So as a result, for example, if you take the sphere, then, okay, so this will live in H3 of S3, so just an integer, then this twisted topological K-theory will be either Z in the even case, or Z mod your chosen integer in the odd case.
What does it mean, gluing function twisted by lambda?
How do you twist?
Is it like something with a gerb instead of like twisted sheaves? Or so then you need the GM, H2 GM.
Yes, H3Z is the same as H2U1.
Okay, H3Z, H2X U1, and then you can use twisted sheaves. Okay.
Thanks. Okay, so this was a topological introduction to the story. Any more questions? I'm still slightly puzzled by the previous question, but I think the bot periodicity tells that you were right and I was wrong. So sorry about that. Okay, so I'll be very vague when talking about the algebra geometric version of the story because, well, first of all, you have heard something about that this week, but also it's much harder than the topological story. So let me assume, at least for simplicity, that X is a smooth scheme over a field. Forever in this talk. So one might ask whether some generalizations of this theory apply in the twisted case too, and the answer is probably yes, but we have not developed that. So for example, there was a Elden's mini course on the Motivic homology of singular schemes, and one might ask if those ideas can be applied here. Perhaps yes, we did not have time to think about that. So for us, we'll work with smooth schemes over a field. And okay, so there's a Motivic spectral sequence, which is supposed to be reminiscent of the Atiyah-Hirzebruch spectral sequence, except that one decided to re-index everything, so the indexes look quite different. But, okay, so you take Motivic homology, and it converges to algebraic theory. Again, one might ask where this story comes from. While these groups are much more complicated, the ways to think about this spectral sequence, however, also come from the ways I have mentioned. So one is a geometric version of this skeletal filtration, which is, okay, the comparison is rather vague. So this is not a direct generalization, but I like to think of this as what happened when one tried to do skeletal filtration and ran into more issues. So it's the Homotopy filtration, which was constructed by Brauer and Levine. And so you can think about its terms as higher Chow groups, and in particular, so if you look at H, so certain terms here, these are just the usual Chow groups. So just codimension Q subvarieties in X modulo rational equivalence, and you can, roughly speaking, think about these guys as Q cells, and then think of this as related to the skeletal filtration vaguely. And
but the filtration by dimension of support gives something completely different here.
well, you kind of do. So there's this homotopy Koneva tower. If there was no word homotopy, you could do the Koneva tower, which is actual version of the skeletal filtration. And here you also multiply X with the cosimplicial object and take into account cycles that live on X times AN, where this N differs. And this is this homotopy, which makes it more tricky.
Okay. Then it's 9.
Okay. The second version, the Motivic version of the second approach is, however, a more straightforward generalization, I think. So this is the so-called slice filtration. Which was introduced by Vygotsky. And so the idea is that you kind of want to do the same thing as the slices there, but so since you were looking at, okay, so there appeared double suspensions, so you might as well look at suspensions with two-dimensional sphere and then replace it with the Riemann sphere and think of this as algebra geometric version of the sphere. And okay, so it should rather be reminiscent of S2. And then instead of, okay, so in case someone missed some of Riome's lectures. So, okay, instead of usual spectra, you can look at Motivic spectra in the A1 homotopy invariant settings. And so And so instead of topological K-theory, you'd look at the spectrum that represents algebraic K-theory over smooth schemes. It will be a one homotopy invariant, so you're good to go. And finally, instead of Algebraic-MacLane spectrum in topology, you can take Motivic Algebraic-MacLane spectrum, which represents Motivic homology for smooth schemes. And okay, so what happens to this Whitehead tower business? Well, there is. Can you read this? No, you cannot. Okay. So you can consider the Whitehead tower with respect to, instead of usual connectivity, well, roughly speaking, you do it with respect to P1 connectivity. I mean, one has to make sense of this, but it is as close to reminding usual connectivity when you want to think of projective line instead of the sphere. So this is an honest analogy. And so the hard theorems that relate these two approaches and give you the Motivic spectral sequences are that, okay, first of all, if you use this slice tower, it's called, or slice filtration, then the slices of KGL are what you would want them to be. So, sorry. What do I want to say? Suspension. So you'd want them, instead of the double suspension of the Algebraic-MacLane spectrum, you'd want a usual suspension of with respect to P1. Someone must be happy at this point. And so this gives the atomic spectral sequence. And so a really hard result in this context is that these two different approaches agree in the geometric settings. Okay, so this was the non-twisted version. Oh, and then maybe last remark in the non-twisted case is that is that it's good to think of this Motivic story as an integral refinement of the Grothendieck-Riemann-Roch theorem, because so rationally this spectral sequence degenerates on the second page. And so in particular, if you look at just at what contributed to K0, you just get the rational Chow groups, which you must get from Grothendieck-Riemann-Roch theorem. Okay, so that's all the untwisted story. Any questions so far? Okay, so what I want to talk about today is the following result. So when you have a smooth scheme, and if you either assume that it's characteristic 0 or in positive characteristic if you invert the characteristic. And if you take an Azumaya algebra over your scheme, I will later recall what this is, but let me just... So this is something that you can twist algebraic vector bundles with. Okay, so whatever you can twist your vector bundles with, hence twist K-theory. So then there is a twisted Motivic spectral sequence. A twisted if you chose and Azumaya algebra. And okay, it looks pretty simple. You put A everywhere, and then I will say more about these groups in a bit. So this is something that is built out of A twisted vector bundles. If you take it rationally or étale locally, then your Azumaya algebra will trivialize, and so étale locally it is the usual Motivic spectral sequence. Okay. So rationally it's also the same thing. So it only differs integrally and before you it tells you if you find anything. And let me see here. So such a spectral sequence was already obtained by Bruno, Kahn, and Marc Levine, as I mentioned, and the difference is that they assume that the Azumaya algebra comes from the base field. So there are less possible twists. And also, they use the first approach, so this homotopy conveyor filtration, and so they have to prove moving lemmas, and there are different tastes in mathematics. There are some people who love proving moving lemmas. I guess they coincide with the people who can prove moving lemmas. Okay, so they use approach one. There are also different kinds of people. So we will be, okay. There is injustice here. So we use the second approach, so no moving lemmas for us. What we then have to do is, we have to define twisted Motivic homology in a different way, and then compute the slices of twisted K-theory as this twisted Motivic homology. So and to do that, okay, so to define this guy and compute this story, we use on one hand certain deep structural results in Motivic homotopy theory, which I will not recall so much. So something about how Motivic spectra behave, but also there is a concrete geometric input, which I will explain in the end. So just something simple from the world of birational geometry, which you will hear about in the end if you stay tuned. So I will now recall what is twisted K, or recall, define, whatever, what is twisted K theory and what do we mean by these twists, and then say a bit about this. Any questions so far?
Sorry, more? Is there some a priori meaning I should assign to this ZA minus Q, or is it by definition the slice? Or?
Where is minus Q?
Well, forget the minus Q, the ZA.
Okay, so good question. So I will tell you how to think about ZA. So ZA will make sense. It will be a certain sub-sheaf of integers. And then this guy is actually, so let me say a bit about it. So on one hand, this will make sense in 5 or 10 minutes as a sub-sheaf of integers. So this is a concrete thing, and one can take the then one can wonder, okay, how to use this to define the twisted Motivic homology, and actually maybe let me write it here. So suspense, there will be meaning given to the A, and then given this meaning, so it will be a subsheaf of integers. And so what Kahn and Levine do, what?
Subsheaf in the Nisnevish topology?
Yeah, there is, yeah. Okay, so with that in mind, one can then, in different ways, to define twisted Motivic homology. And so what Kahn and Levine do, which I think is a nice construction, except that it works when Azumaya algebra comes from the base field, and we could not prove that it works in general. But since it's a nice construction, let me tell you about it, and then I'll tell you mention what we do. So what they tell you to do then is, if you want to define twisted Motivic homology, they think of them as of twisted Chow groups, or twisted higher Chow groups. You just look at this, usual Chow groups or higher Chow groups are defined as taking cycles with integral coefficients, and they just say that, so you would usually take some pre-abelian groups on some algebraic cycles, and they just say, okay, so instead of this integers, think of integers as the sheaf of integers that you computed at your cycle, and replace it with the value of this funny subsheaf. Okay, so this is a rather explicit construction. So you will have less possibilities for which coefficients to take, but then it will define the complexes, and you can take its homology groups and get twisted higher Chow groups. And this works when A comes from the base field, and possibly more generally, but we don't know.
Yeah, there is another, it depends which kind of moving lemma approach you use, but there was this proof of Yakerson conjecture for Azumaya algebra by Suslin and so, in the late 90s, and this uses a moving approach. It could be maybe used, I'm not sure.
See, you can see a person who knows how to deal with moving lemmas. A typical example. Okay, so speaking of other people, so to define this twisted Motivic homology, we think about HZ as a Spitzwegs Motivic homology spectrum, which is this Motivic homology spectrum that satisfies base change, and there was a beautiful theorem by Marc that tells you that if you think of, okay, I'll say something in the next minute which it doesn't make sense to you, just forget about it, but in case you have heard about the theory of Motivic spectra with frame transfers, so Marc tells you that if you think of it in that realm, then you can, so as a framed Motivic spectrum, Motivic homology is just the frame suspension spectrum on integers. So if you think of integers with respect to an extra structure of frame transfers, this is just that. And so what we then do is we just define this as taking that construction on this subsheaf. So this is, on one hand, this is more abstract than this construction. On the other hand, it's more universal and easier to compute slices of.
Mara, in this case, A it must be defined after the base field then.
Why?
Because don't you frame transfer things that live on the base field? I mean, you need something like a sheaf of something defined on the front.
You can.
No? I mean, you're the expert, so I mean.
No, you can do it in. You can indulge yourself into the fact that the theory of, okay, maybe I should put here free. That's. Okay. So there is, okay, so this whole business uses the fact that, so for Motivic spectra, they are the same as Motivic spectra with frame transfers over any base. So. Okay, so I'll be kind to, if I were sitting in the audience, I would hope that someone reminds me what all these twisted things are in the algebraic sense. So I will say a few words about what it is. So, okay, so maybe the motivation, one of the motivations for why people care about twisted K-theory at all is that if you try to compute K-theory of a Brauer variety, then it decomposes so as the product of twisted K-theories of the base field. So maybe if a priori you were interested, what I'm saying is that if a priori you were interested in classical algebraic K-theory, no funny business, but then you looked at it of several Brauer varieties, then you might want to understand twisted K-theory to do that. So this is just one of the, I think, standard motivations. And so, okay, so what these objects are. So an Azumaya algebra of degree D. So this is. So it's a sheaf of quasi-coherent X algebras that on affines is a tau-twisted form of the matrix ring. So Okay, so this D is the degree. And so they're classified by étale PGLD torsors. And the main example, the simplest example, is that quaternions are a degree 2 that's my algebra over real numbers. And then, so to get to the twisted vector bundles, so you can consider the stack of twisted vector bundles. Okay, and a simple way to think about it is that on affines, this is just finely generated projective modules over your Azumaya algebra. And so, good thing about it is that while this is a more refined thing, once you look at the twist vector bundles, they only depend on the Brauer equivalence class of A. So this thanks to a Morita equivalence, will only depend on the Brauer class, and so this means that, okay, so there's an equivalence relation on Azumaya algebras that gives you the Brauer group, and so two Azumaya algebras are Brauer equivalent if okay, I'm doing this again for smooth schemes over a field. So in more general worlds, there are different versions of the Brauer group. I'm not going there, but if you're interested, Brauer groups are great. There's a lot to learn and very enjoyable material. But okay, we'll stay down to earth. So for us, two Azumaya algebras are Brauer equivalent if they're vector bundles such that if you tensor with their endomorphisms, you get, so this A and B are the same up to tensoring with endomorphisms of some.
Vector bundles everywhere of positive rank.
Okay.
Otherwise it's zero, then you get zero.
Okay. Okay, so so with that said, now that we know what twisted vector bundles are, we can easily define twisted K-theory. So this is just the Zariski sheaf of spaces, which on affines will be given by the group completion of the A twisted vector bundles. Because we're working over for smooth schemes, things are not too bad for us. So this is and it will be a module over untwisted K-theory.
So what is your vector A group?
Yeah, so you take this space stack of A twisted vector bundles. It has direct sum as an operation, which makes it an infinity space. You can take its group completion, and this is what twisted K-theory is on affines. And you want to define it more generally as if you're lazy like me, then you just define it as the Riskification of this thing. But then in the finds, it will actually be given by this thing.
Is there a good example to keep in mind, like P1 and H over R?
Example of what?
Like, could you actually compute it for K of P1?
Oh, you should be able to. You should be able to. There is a paper by my ex-advisor in St. Petersburg on K-theory of Severi Brauer varieties, and I think there you have examples. And I think I could write it out and make a mistake. So.
Can it also be defined as like the K-theory of the perfect, of the category of perfect complex?
Yes, sure. Yes, it makes sense. So yes, more abstractly, people, you're so amazingly abstract-minded that yes, I could have never spoken about vector bundles. Sure, you can take A twisted perfect complexes, do Thomason's construction, and be happy. Yes. More questions? What?
Can you twist the whole aspect?
Ooh. Oh, dash is aren't you? Can you? Why not? I mean, let me think. I will not say anything meaningful, but I'll think for 2 minutes, and then we'll continue the talk.
What's your question?
Yeah, I mean, why not?
What's your question?
The question was whether it can be adventurous and twist not just K-theory space, but the whole category of spectra. And I thought, yes, Matthew says no.
I mean, it should be much harder than twisting cohomology.
Yeah.
It's possible.
But I mean, cohomology. Motivic homotopy can be twisted.
Yeah, so I'm waiting for you.
Yeah, but then I wonder, can you do another
But can you twist any localizing around it?
Yeah, because
Yes.
it's perfect, yeah, that's fine.
Yes, there are complexes you can twist in it.
You mean a version of SHX twisted by this A?
Yes.
Okay, so my current answer is I would not know how to do that. Okay, I'm trying to get to this ZA, the suspense I promised you. That's a funny thing, so I want to get there. So let me remind you that before we did twist, there was a standard thing. So there was a rank map, so it was something that associated to a vector bundle on something connected a number. So it induced the rank map on K-theory. And so in the twisted case, there is, one can define what is the twisted rank map, and its image will live in this funny thing. So in this sub-sheaf of the integers. Okay, so if you were to define it, you can define a formula that sends, okay, let's say we're on the finds, so you take this A module and then send it to the square root of the rank of the endomorphisms. And so if you took the A itself as an A module, you should get the degree of A. And so why the image will be some subsheaf? Well, on a local ring, so if you take a local ring, then you can compute that the image will be given by the index of your Azumaya algebra. Where the index, So this is the GCD, the greatest common divisor of all Azumaya algebras, of degrees of all Azumaya algebras that are Brauer equivalent to your chosen one. So, for example, if you looked at quaternions as the simplest example of a non-trivial Azumaya algebra, then on complex numbers it would be the whole integers, but then on real numbers the value would be the even integers.
Should it be NOP rather than NAP?
What did I do wrong with my life? Where? What?
Confused. There's a rank of NAP or NOP.
I think I want to do this, but you can do whatever you want, but try to check that the class of the algebra itself is sent to the degree. So if you do O and A, you'll get different numbers, and you want this one. I think it's A. Last time I checked, it was A. I may have made a mistake, but I hope it's A. But I do occasionally wonder about this question. So. Okay, so this sub-sheaf is kind of funny. Well, it looks maybe somewhat random, but actually this is, okay, so facts about this, the image. So if you define it as the image of the twisted rank map, first of all you'd get that this is the, so this guy is in fact the shiftification of the twisted K0, which is good because in the untwisted case, shiftification of K0 is just integers, so it's good that we get that. And then it has, so while it is not a constant sheaf, it has a bunch of nice properties which are all used in our proof. So it is a one homotopy invariant when the base is regular. And so another nice feature of it is that it's a birational sheaf, which means that if you have a dense open embedding, its value won't change. And also it satisfies rigidity. So if you have, say, local ring, then it will be the same as value on the closed point. And okay, what?
Zerian local.
Yes. It may have more nice features, but overall I think it's a funny, interesting subsheaf of the integers. And okay, I have 10 minutes left. I should actually tell you how we prove something. Any questions so far?
I have a bit confused where you're saying it's subsheaf of integers. What am I supposed to do it as a sheaf on? Is it on smooth K-schemes?
So if your A came from the, if this was an Azumaya algebra over K, then yes? Yes, smooth K-schemes.
But on any fixed connected smooth scheme, it's constant, right?
It is a risky sheaf, not as an Isnevich sheaf.
Right, as a risky.
It's not constant.
Yes.
But by rational invariance, if I pick any open of my smooth, it takes the same value as on the whole thing.
But for the cycles, you take the value at the generic point, at the generic point of the cycle, which is the kind of the enzylization. If you want to enzelize you take the Enzelian local ring at this point, so you don't get the same thing as for the.
And maybe the
Yeah, that okay, it's not necessarily constant. Yeah.
on the big side it's not constant.
No, sure, but on each individual smooth thing, it's Zariski constant.
Yeah. I think you're right.
Okay, but it's
I
not
have-
necessarily constant.
yeah.
Okay.
I need to tell you an actual input that we used in the proof. Otherwise, you will blame me that I just defined things that were known for years and then I'll be never invited to a summer school at HES again and never take the rare B, which is broken in the middle of the line. No, this cannot happen. Okay, so besides all the abstract theory of Motivic homotopy theory, the thing that is useful for us is that there is a fiber sequence of A1 homotopy types which is that if you look at this twisted rank map, then, so if there were no twists, I would put here stable vector bundles, which up to A1 homotopy are the same as the infinite Grassmannian. And so luckily for us, one can do the same thing with twisted Grassmannian, where this guy parameterizes A twisted vector bundles with an embedding into A infinity, where A stands for this beautiful A. Okay, so this should not be too surprising if you have seen this thing in the untwisted context. In fact, in the untwisted context, there is a splitting given by you take your number and you send it to the class of the trivial vector bundle, and so this gives you a splitting. And so the surprising thing is that, or I don't know, maybe not surprising for you, surprising for me, is that when A is non-trivial, then this sequence does not necessarily split globally. So this. So Zariski locally it does, and then globally may not. May not split globally. And so this is a difference in terms of what you'd want to prove afterwards. So in the Motivic settings, it is a very useful fact that K-theory space as an A1 homotopy type has this very nice geometric model given by the infinite Grassmannian times integers. And here we're a little stuck in this fiber sequence. And okay, but I wanted to say, so why we don't actually have a proof? Well, I don't know. It should not split globally always. And the reason for that is that there is a very beautiful work by Ben Antio and Ben Williams, which tells you that. Okay, so the fact that I'll write down now does not exactly prove that this doesn't split, but it gives you an sentiment. So they show that they give examples of schemes. So they provide explicit examples of, say, a 6-dimensional smooth affine scheme where the index is not realized by any Azumaya algebra. So the index was this GCD, and they say that there may not be And it's a my algebra such that its degree is the index.
For local or semi-local.
Yeah. Locally, always good. Yes, that's why I said. Yes. Locally, Zariski locally does split.
Does it split Zariski locally?
Yes.
Why?
Because over a local ring, you don't have that many Azumaya algebras. You have this generator. I forgot how it's called. Well, you have one specific generator.
Yeah, but for the Zariski topology, it's but not Nisnevic.
Yeah. Sorry, Zariski locally.
Yeah, so as Zariski sheaves, it splits because Zeta is very simple.
It splits Zariski locally, but we cannot say that this is the product of these two guys.
It splits only when you split, but not Zariski locally for the Nisnevic topology. It doesn't split for Zariski local ring in the Nisnevic.
I have, wait a sec, I think I had an answer to your question, but I forgot how to, there is a name for this. Okay, whatever. Okay, I cannot say more than I did. So if you plug in, if you evaluate these things on a local ring, then there will be a splitting. However, if you look at them as Evan homotopy types, you cannot write that this thing is a product of the other two. And mainly because you don't know you don't have a canonical representatives to send your index to. Okay, so this is an issue which makes our paper not just put A everywhere and be happy. However, this is good enough. Okay, so the corollary is that, so this is good enough to see that although it doesn't split, nonetheless these two things are stable under pullback. So this twisted K-theory satisfies Milnor excision and CDH descent. As does any Motivic spectrum that is stable under pullback. So this is why we're happy that there's this geometric model here, because for Grassmannians it's easy to see that it is stable under pullback. So let me tell you the main geometric idea for computing slices. Okay, so main the theorem. So to prove the theorem, you use this proposition, and so how? Okay, I'll just say in the last minute how to use this proposition to compute the slices. Well, by what periodicity you just have to compute the zero slice. So you want to show that this so the map from the effective cover of K-theory to twisted Motivic homology is a zero equivalence. And then there is a work by Elden and Tom Bachmann, which tells you that over a perfect field, this statement is in fact equivalent to asking that our beautiful rank map so this is the zero slice. So after you apply, okay, so I want to say that zero slice of this guy is this thing, and in other words, it's the same as saying that this is just rewriting. Think about the fact that I want to prove that this is, so S0, I want that S0 of KGLA is HZ. Okay, so this is what I want. And I don't want just an abstract isomorphism. I actually have a concrete map from one thing to the other, induced by the twisted rank map. I want to look at this thing. And okay, so wait, don't listen to me please for one more minute. So they show that this abstract statement is equivalent to saying that this is a birational equivalence of A1 homotopy types. So enough to show that this is a birational equivalence Okay, and so what does it have to do with anything? Well, the typical example of a birational equivalence is the embedding of GM into, so A1 minus point into A1, and then the cofiber is A1 mod GM, which up to one homotopy is equivalent to projective line. And so this guy is, well, P1 one connective. So if you think about this being the main example of birational equivalence, then this would be something that induces zero equivalence, and they actually prove by, so they actually prove that, I don't know why I wrote them in the opposite order, but that all the S0 equivalences are given by, well, generated by suspension spectra applied to birational open embeddings of smooth schemes. And so, which finishes the main thought that I wanted to tell you, because we now look here at the sequence and see that the difference between them was given by the twisted Grassmannian, but the twisted Grassmannian, just like the usual Grassmannian, has a dense open cell, which is isomorphic to infinite affine space, so it is in fact a rational space, so birationally trivial. So we're lucky that this infinite Grassmannian has an dense open cell, which is an infinite affine space. So then, using this fiber sequence and this geometric approach to expressing slices, we're happy.
So the infinite Grassmannian here, is it an in scheme or a
yes,
scheme? Or
in scheme.
Namely, you take.
Yes.
Any further questions?
You said to compute these slices, you also need some structural results about Motivic spectra. Would you mind saying a little bit about that?
Well, first of all, the definition. So our definition is this thing. And to do this, we use this deep result by, okay, it's not very humble to call it a deep result. Okay, a deep extension by Markova of our result on comparing spectra and Motivic spectra. So there is a lot that goes here, and roughly speaking, you should read this abstract amount of letters as if you consider cohomology theories as, okay, so this says two things. All cohomology theories that are represented in Motivic stable homotopy category have an extra structure of certain kind of transfers, which is unique. And if you take that into account, then many things become simpler to define. So this So this is like Spitzweck's Motivic homology spectrum, which is a difficult thing to define. And then when you look at it in the more complicated category, then it has a much simpler construction. Just suspension spectrum on integers, but this is if this was a typical suspension spectrum, this would just be a sum of several sphere spectrum. This is not what I mean, because there is this extra input. So even defining these things in such a way already requires a lot of background results. And then, okay, once you have that, you can look in our paper. I mean, I think I told you guys the part that I find accessible and nice to retell. And then, okay, there are technicalities to check which use, in particular, the theory of frame transfers and also other theories about slices, like are the results about slices and their properties and okay.
With one Motivic homology is usually supposed to be something like the Picard group weight. So is there any geometric meaning of the weight Motivic homology in this context? It's sort of twisted Picard group weight. Do you know anything about that?
We thought about it. I don't remember coming. I feel bad. And then we discussed it, and I can't remember an interesting answer that we were able to prove. We had a conjectural description that we were not able to prove. So I don't have an answer. This is an interesting question, and maybe someone else has an answer to that. There should be indeed a description.
How did you prove that this recovers the Kahn-Levine spectral sequence?
Yes. When the Azumaya algebra comes from the base field, this is the same spectral sequence.
And how do you do it?
How do what?
How do you do it?
Well, I think the main idea is that using the Levine's result that's less filtration is the homotopy conjugate filtration. So.
Right, but this is defined in another way. That seems a difficult thing to do, isn't it?
Yeah.
So you mentioned you mean that spectrum sequence I identified, but maybe there's some stronger statement to which identify future spectra. I don't know whether you have any.
So wait, no. So what this amounts to is understanding that when the Azumaya algebra comes from the base field, then there's this description of Motivic homology groups in terms of the Chow groups that they described. And that follows from using earlier works, mainly by Marc. It is provable. It's also the proof is written in the paper. I have looked at it 1 hour ago. Can I say? I mean, there is not too much work, extra work that goes into it.
Not much.
No. I mean, Marc has done lots of work over the years, and then you use Marc. And use...
Which Marc?
Levine, Marc Levine.
Okay.
The Ka and HA oriented?
Yes. So this Ka is a module over... KGLA is a module over KGL. And yes.
But it's not a ring.
Yes, okay, the best thing so KGLA is a module over KGL. It doesn't have a ring structure. Sorry. Yes, that's...
It also could be a ring.
Yes, but then I think it is because it's module over KGL, so it should be. Yeah. Oriented in a non-ring spectrum sense.
Does it work for derived Azumaya algebras?
It would work if we were less lazy to write it down. It should work. I think we have a remark in the beginning saying that it should work.
What's abstraction? Okay.
I don't have enough PhD students to write it down. I don't know. It should be, so first of all, it should also work for Brauer classes that don't come from Azumaya algebras and for derived Azumaya algebras.
What is derived Azumaya algebra?
Talk to this guy.
It's an invertible module over the symmetric monoidal category given by the category of perfect complexes over this cube. So it's a symmetric monoidal category. Then you can consider modules over this, and you can consider invertible modules over this. Yes, this would be one definition.
So as far as I understand, they're better than usual ones because they get rid of the discrepancy between Brauer groups. Do I remember?
Yeah, so any Brauer class is represented.
Yeah, so that's one should in fact think about derived Azumaya algebras and not. But it's a summer school, so one can give talks that are actually understandable.
And like regarding the basic theory rather than this slight coefficient, does it work also like with x replaced by a general scheme?
No, not to our current understanding of things. A lot of things here use that x is smooth. In particular, well...
And we also have like SHS for general S.
Sure. However, so first of all, there are experts of Motivic homology of singular schemes in the audience. But before that, so I think Elden's mini course was roughly speaking dedicated to the idea that constructing a Motivic spectral sequence for singular schemes is more complicated. It requires extra inputs. It's not the right thing. So if you take a singular scheme, you should not just have the same spectral sequence. However, I think what you should get is like, so Elden and Matthew construct this K-theory of singular schemes from the CDH Motivic homology and inputs from TC, and if you there replace this CDH Motivic homology with twisted Motivic homology and take the same inputs coming from trace methods, as I discussed with Elden this morning, you should get the right thing. However, no one has checked it since this morning.
You need twisted symptomic cohomology.
So according to Ellen's musings of this mornings, you don't, but I would not rely on those. So you can think about it.
So of course, instead of Azumaya algebra, you can consider twisted sheaves for a gerb, and this doesn't require to have a global Azumaya algebra.
Yes.
I don't know if it is the same as...
It is.
It is the same as your... Okay, so it's not really... But on the other hand, for a gerb, you can consider the kind of the stack of trivializations of the sections of the gerb. So this is automorphism, everyone is GM, but this is like line bundles, but unlike line bundles that you can tensor, here you cannot tensor. On the other hand, you have some Motivic homology which replaces R gamma GM, which so you have something else for which you can do or add. So it seems to, but there should be a way to get this Motivic, like this was one of the questions, to get this Motivic. It looks like that you change the complex, giving you change it by putting ZA, like the complex from rational functions to divisor, but that's putting divisibility by the, this is the multiplication of the chart group of the, I'm not sure.
I think that there are two groups of questions that can be united. One is how to generalize it to derived stacks over anything, and the other is how to twist by more general things, and those questions come together. So the more general things you consider, the more you have to upgrade the concept of what you're twisting with. When you're looking over a smooth scheme over a field, I think twisted with an actual Azumaya algebra is good enough. However, then when you generalize this, you might also.
So there was a question of describing the weight one, which is just R gamma X GM. The weight one, which is the R gamma X GM, it's replaced by, the weight 0 is replaced by ZA.
Yes.
The weight 1 is replaced by what?
Vov asked about that, and I did not have a good answer. I believe there should be a good answer. I don't know of that. I don't think, as far as I remember, it's not in the literature. But it's a very good question.
It could be so you have the Nisnevich complex, which is does the Gerson resolution of GM, but putting the condition, putting this integer multiples. Okay, I'm not. I have to think.
Well,
we can all think about this afterwards. So let's coming again for her talk.